We are going to be learning about trigonometric substitution, and what this is going to do is enable us to solve a class of integrals that as of now we don't have a method for evaluating. First of all, let's look at a half circle, and we know that the equation for this half circle would be y equals square root of a squared minus x squared if a is the radius of the circle. So if we were interested in finding the area under this curve using calculus, we could integrate from 0 to a. But if I tried to evaluate this integral, trying to think of an antiderivative, we would have the chain rule apply, and we have this x squared here. If we tried to let that be our u, our du would be 2x dx, and that's a function of x that we don't have. Also, very soon we're going to be learning arc length, and the length of a curve from A to B will involve an integral that will have a radical, and it will have a number here with a plus and something squared here. So if we know how to solve integrals of this form, that's going to help us. So let's first look at integrals that involve a square root of a squared minus x squared. Now, if we make a triangle, we could label the hypotenuse A, and we could label this side x. So what would this third side be? Well, that side squared plus x squared would equal a squared by the Pythagorean theorem. And so s squared is going to be a squared minus x squared. And then we could square root both sides, and we're only interested in the positive root because it's the length of a side. So that side would be the square root of a squared minus x squared. Now, if we put theta on the triangle, what trig function would relate the two easier sides, the x and the a, to theta? Well, sine theta is opposite over hypotenuse. We could then multiply both sides by a and have x equal a sine theta. This is a substitution then that is actually going to help us evaluate integrals that have something of this form here. Now, if we use this substitution, we're going to use the substitution, do the integration, and then we want to be able to resubstitute. So we want this substitution, the function we're subbing in, to be a one-to-one function so that it has an inverse function. So we can go forward with it and then come back again. So we are going to restrict theta to be from negative pi halves to pi halves so that it is one-to-one. And this is the same restriction we use for inverse sine. Now let's see how all of this would work. So here we have an integral, and it involves an a squared minus x squared underneath the radical. We can see it here in the denominator. And so we're going to draw a right triangle. We are going to label the hypotenuse 4, because 4 squared will give us this 16. We're going to label this side x, and then the other side would be the square root of 16 minus x squared. So if this is theta, we know that sine theta is going to be opposite over hypotenuse. We could multiply both sides by 4, and we would have our substitution, x being 4 sine theta. Now if we go ahead and do the substitution here, we can see that we need dx. So let's go ahead and find dx. That's going to be 4 cosine theta d theta. So we're going to replace x with 4 cosine theta d theta. And then we're going to rewrite in radical form. So this is going to be 16 minus, here's our x. Our x is 4 sine theta. It needs to be squared. So 16 sine squared theta, and then that needs to be cubed. So looking at this, let's work on simplifying the denominator. I have this radical, and I've got the 16 that I can factor out. That'll leave me 1 minus sine squared theta, and that's still cubed. Now we can take that, and we can replace the 1 minus sine squared with cosine squared theta. All of that's underneath the radical, so we could square root the 16, that would be a 4, and we could square root the cosine squared theta, that would be a cosine theta, but it still has the cubed on it. So now we have worked the denominator and gotten it down to 4 cosine theta quantity cubed. Now looking at that with the numerator, I can cancel the numerator with one of those. So what do I have left? Well, I have 1 over 16 cosine squared theta d theta. But in looking at that, I can bring the 1/16 out in front, and 1 over cosine squared, well, that's just secant squared theta d theta. Oh, well, I know the antiderivative for secant squared theta. So I can now work this integral. The derivative of tangent theta is secant squared theta. So this is 1/16 tangent theta plus our constant of integration. Well, we're almost there, but we're not done because we need to resubstitute and get this back in terms of x. So what is tangent theta? Well, let's look back at our triangle to answer that question. We know tangent is opposite over adjacent. So our final answer here, we've got x over, and the 16's on the bottom, and then that adjacent side is 16 minus x squared, and then plus our constant. So that is how trig substitution works. It enabled us to evaluate this integral that we didn't know how to evaluate otherwise. Now there's a couple other forms in integrals that trig substitution will work nicely for. If we have an integral involving a square root of an a squared plus an x squared, if we labeled the sides of this triangle a and x, and we did the Pythagorean theorem, then we could see that the hypotenuse would be the square root of a squared plus x squared. So if we put theta in this triangle, then if we related the two easier sides to this angle, we would have tangent theta equals opposite over adjacent, solving for x, x equal a tan theta. So for integrals that have the square root of a squared plus x squared, this substitution is going to work nicely. And we would need to again restrict the angle so that we have a one-to-one function. And so we would restrict it from negative pi halves to pi halves. Then there's one other form that would be helpful if we have integrals involving square root of x squared minus a squared. We would label the hypotenuse x, and we'd label this side a, so that this side will be the square root of x squared minus a squared. And if theta is our angle here, trig function to relate the a and the x, secant theta equals hypotenuse over adjacent, solving for x, x equal a secant theta. Restricting so we have a one-to-one function, we're going to let theta range from 0 to pi over 2, then from pi over 2 to pi. So if we have integrals of one of these three forms, we are going to draw a right triangle, label the sides, and come up with the trig function that will work nicely for the substitution. So I don't want to try necessarily memorize this, is get the idea so that I can make the triangle. So you'll want to watch the examples following this so you can see how you can identify what to use, how to label the triangle, which trig function to use in your substitution.